Thermodynamics of ideal gas. Thermodynamics of ideal gas. So in the last session, we derived an expression for log omega, and in the asymptotic limit, log omega is nothing but log gamma, and it is nothing but log sigma, and it is approximately equal to n. What is equation? N log V by h cube 4 pi me by 3n whole raised to 3 by 2 plus 3 by 2n. This is our equation, 3 by 2n. What is entropy? Entropy is k log omega. So that is equal to nk log V by h cube 4 pi me by 3n raised to 3 by 2 plus 3 by 2n. This is the equation for entropy. This is the equation for entropy. Now, I can multiply this with 2s by 2 by 3 nk. 2s by 3 nk. What is 2s by 3 nk? What is 2s by 3 nk? It is 2 by 3 log V by h cube 4 pi me by 3n raised to 3 by 2 plus 1. Is it clear? Okay. Multiply with 2 by 3 and divide with nk. Then the final term becomes 1. Here it becomes 2s by 3 nk. Here this nk will cancel and you will get a 2 by 3. Or 2s by 3 nk minus 1 is equal to log of v raised to 2 by 3 divided by h raised to 2 plus log of in log ab is log a, or I will write it as log of v raised to 2 by 3 by h square into 4 pi me by 3n. Here I used the expression log a raised to b is b log a. Okay, b log a. Here b is 2 by 3. 2 by 3 log of a quantity is actually log of a raised to b. So log of v raised to 2 by 3. H raised to 3 whole raised to 2 by 3 becomes h square. 4 pi me by 3 and whole raised to 3 by 2. That raised to 2 by 3 that becomes 4 pi me by 3. Okay. Now take exponential on both sides. So e raised to 2s by 3nk minus 1 is v raised to 2 by 3 by h square into 4 pi me by 3n. My aim is to write an expression for energy. My aim is to write an expression for energy. Okay. So what is the value of energy? What is the value of energy? E is h square divided by v raised to 2 by 3, 3n divided by 4 pi m e raised to 2s by 3nk minus 1. Okay, keep this e here, take all the terms to the left hand side, then you will get e as this. Call this as equation 1. Call this as equation 1. Once you have energy, then we have this thermodynamic relation. T is equal to dou E by dou S at a constant N and V. From where I got this expression? We already have from thermodynamics dE is equal to TdS minus PdV plus mu dN. This is our expression in thermodynamics. Call this as equation number 2. At a constant N and V, dE is equal to TdS. So T is equal to dou E by dou S at a constant N and V. So take the derivative of this equation, equation 1, with respect to S. this much term, these are all constants. 3n by 4 pi m, these are all constants. E raised to 2x by 3nk minus 1. Derivative is exponential e raised to 2x. Derivative is e raised to 2x into 2. In a similar manner, you have to write the derivative of exponential 2s by 3nk minus 1. It is e raised to 2s by 3nk minus 1 into 2 by 3 nk into 2 by 3 nk. So t is equal to this entire time, initial time is nothing but e, remaining is 2 by 3 nk. So I can write it as e is equal to 3 by 2 nkt. Call this as equation number 3. E is equal to 3 by 2 nkt. If there are n moles of the gas, I can write it as E is equal to 3 by 2 n into Na kT, because total number of molecules becomes n into Avogadro number. Each mole of gas consists of Avogadro number of molecules. So capital N becomes n into Na, and I can write it as 3 by 2 nRT. 3 by 2 nRT. Okay, this is equation say 3a. 3a. So energy, I can write it as 3 by 2 nkt in terms of Boltzmann constant, or I can write it as 3 by 2 nRT in terms of universal gas constant. Universal gas constant. This is the internal energy of an ideal gas. Internal energy of an ideal gas, and it depends only on the temperature. It depends. So this is one of the thermodynamic quantity we are looking for. Now we have specific heat capacity at a constant volume, Cv. Cv is nothing but dou E by dou T at a constant N and V. Specific heat capacity at a constant volume, dou E by dou T at a constant N and V. We already have an expression for energy in terms of temperature. So take the derivative. We already kept this n and b constant. So taking derivative, I will get it as 3 by 2 nr. 3 by 2 nr. So this is equation number 4. Equation for Cv. Equation for Cv. Then I have another expression. Pressure is equal to minus dou E by dou V at a constant n and s. This also obtained from equation 2. Equation 2 will നിന്ന് തന്നെയാണ് ഇത് വരുന്നത്. dE is TdS minus PdV plus mu dN. If S and N constant, then I can write P is equal to minus dou E by dou V. Minus dou E by dou V. So take derivative of expression 1. Expression 1 with respect to V. So V ഒഴികെ ബാക്കി എല്ലാം കോൺസ്റ്റന്റ് ആയിട്ട് ട്രീറ്റ് ചെയ്യാം. So I can write h square 4 pi 3n by 4 pi m 3n by 4 pi m exponential 2s by 3nk minus 1. All these are constants. Then derivative of v raised to minus 2 by 3. Because we all have v raised to 2 by 3 on the denominator. So it is v raised to minus 2 by 3 on the numerator. So P is equal to h square 3n by 4 pi m e raised to 2s by 3nk minus 1. What is derivative? 2 by 3 v raised to minus 5 by 3. This minus and this minus 2 by 3 becomes plus 2 by 3 into v raised to minus 5 by 3. In v raised to minus 5 by 3, I can write it as 1 v raised to 2 by 3 right here, and the remaining v in the denominator I will write separately, because I can write 1 by v raised to 5 by 3 as 1 by v raised to 2 by 3 into 1 by v. Why I wrote like this? This is again, so what, there is a 2 by 3. So I can write it as 2e by 3v. 2e by 3v. P is equal to 2e by 3v. This is equation number 5. Pressure of an ideal gas is 2 by 3rd of energy density. Energy by volume is energy density. So pressure of an ideal gas is 2/3 of energy density. We already derived this one without the explicit calculation of omega. Okay, നമ്മൾ കഴിഞ്ഞ ലെക്ചറിൽ നമ്മൾ ഒമേഗയുടെ എക്സ്പ്ലിസിറ്റ് വാല്യൂ കണ്ടുപിടിക്കുന്നതിന് മുന്നേ ചില ലോജിക്കൽ ആർഗ്യുമെന്റ്സ് വഴി ഈ എക്സ്പ്രഷൻ ഡിറൈവ് ചെയ്തിട്ടുണ്ടായിരുന്നു. P is equal to 2/3 of energy density. Okay, now we obtained it from an explicit relation for omega. Okay, now you can write from here E is equal to 3/2 PV. 3/2 PV. So we already have E as 3/2 nRT is equal to 3/2 PV. Okay, from 3. Okay, you substitute for E. What is E? 3/2 3A. 3A from 3A. You write it as 3/2 nRT equal to 3/2 PV. That is PV is equal to nRT. This is ideal gas equation, and call this as equation 6. PV is equal to nRT, ideal gas equation. Now I can calculate the specific heat at a constant pressure, Cp. Specific heat at a constant pressure, that is nothing but dou by dou T of enthalpy at a constant N and P. What is enthalpy in terms of energy? It is E plus PV. E plus PV at a constant N and P. Now, what is E plus PV? What is E plus PV? It is dou by dou T of E is actually 3/2 nRT. PV is nRT. So I can write it as like this. So it is dou by dou T of 5/2 nRT. Taking derivative with respect to T, you will get it as 5/2 nR. So Cp is 5/2 nR. Call this as equation number 7. We already have an equation for Cv, equation number 4. Now we obtained an expression for Cp. So I can calculate the ratio of specific heat Cp by Cv. It is 5/3. 5/3. Because one is 5/2 nR, the other one is 3/2 nR. So the ratio is 5/3. So the ratio of specific heat for an ideal gas is 5/3. Now suppose the ideal gas undergoes an isothermal change. Suppose gas undergoes an isothermal change. What is mean by isothermal? Temperature is a constant. T and N constant. Number of particles is always constant because it is a closed system. And now we are assuming that it is an isothermal change. Okay, temperature is also constant. T and N constant. So since energy is just 3/2 nRT, this will be a constant because it depends only on T. T is constant for an isothermal change. So E is constant. That means P is equal to 2E by 3V implies P is just proportional to 1/V. Because energy is a constant, 2/3 is a constant, so I can write it as P proportional to 1/V, and it is nothing but Boyle's law. It is called Boyle's law. Okay. What is entropy change? What is entropy change? Entropy change, I can write it as final entropy minus initial entropy, SF minus SI. Okay, so delta S is equal to SF is K log omega F minus K log omega I, initial number of particles. Okay, but number of particles depends on omega, depends on N, V and E, but here E is constant, N is constant, so the only variable is V. Okay, so it depends on log V. Depends only on log V. I can write it as delta S is equal to K log omega F by omega I. For N molecules, it will be nk log omega f by omega I, and it is nothing but nk log vf by va, because all others are constant. When you write omega f and omega I, all other quantities are constant except v. Okay, energy and number of particles are constant. So when you divide, you will get simply vf by va. So change in entropy for an isothermal process is nk log vf by va. Now consider an adiabatic process. Consider an adiabatic reversible process. Adiabatic reversible process. What is adiabatic reversible process? That means S and N constant. Entropy is a constant. There is no change for entropy for a reversible adiabatic process. Then energy will be proportional to V raised to minus 2 by 3. That is, energy is proportional to V raised to minus 2 by 3 because we have equation 1. Equation 1. Energy depends on V, N and S, but N and S is now constant. So, E is proportional to V raised to minus 2 by 3. That is from equation 1. From equation 1. Okay. Now, we can write T is proportional to V raised to minus 2 by 3 because E is equal to 3 by 2 nRT. So, energy and temperature are directly proportional. E varies with the volume as V raised to minus 2 by 3 implies. T also varies with the volume as T proportional to V raised to minus 2 by 3. Okay. Then I can write P proportional to V raised to minus 5 by 3. Why? Using the expression P is equal to 2 by 3 E by V. E has a dependence of E has a dependence of V raised to minus 2 by 3 divided by V. That means that some constant, okay, some constant. This is not Boltzmann constant, you put some C. Okay, E is proportional to V raised to minus 2 by 3. So, E can be written as some constant into V raised to minus 2 by 3 divided by a V. So, E is proportional to V raised to minus 5 by 3. Or I can write it as PV raised to 5 by 3 is a constant. This is the equation for adiabatic process. PV raised to gamma is a constant is the equation for an adiabatic process, though we could obtain that relation using this concept. Also, I can write it as TV raised to gamma minus 1 is a constant. Okay, you write substitute for V raised to 2 by 3 from here, this equation T, okay, equation in the substitute here. Then you can write it as TV raised to gamma minus 1 is a constant. So, these are the equation for adiabatic process. Now, we can see that during adiabatic process, adiabatic process means N constant, S constant. Okay. Change in energy is solely due to external work. Why that statement? Because from 2, what is 2? dE is equal to TdS minus PdV plus mu dN. If S and N are constant, then dE is simply minus PdV. And PdV is actually implies an external work done. Okay, an external work done. PdV is a measure of external work done, and so dE change in energy is solely due to external work done. So I can write it as dE is equal to minus of at what is P? P is 2E by 3V into D. 2E by 3V into D. This is the dE for an adiabatic process. Okay. So now we demonstrated how the thermodynamics of a macroscopic system can be derived from the multiplicity of its microstates. That is, from the number of its microstates. Okay. how can we derive the entire thermodynamics from the knowledge of the number of microstates? The equation we derived for entropy, that is S is equal to nk log V by h cube into 4 pi me by 3n raised to 3 by 2 plus 3 by 2 nk, is actually incorrect. Even though we derived some thermodynamic properties using this relation, and all those relations are correct, but there is something missing in this equation. There is something missing in this equation, and we will discuss that inadequacy of the entropy relation in this section. We can write energy as 3 by 2 nkt. So substitute for energy here as 3 by 2 nkt. Then you will get it as S equal to nk log V plus nk log 1 by h cube into 2 pi m kt raised to 3 by 2 plus 3 by 2 nk. Okay. Here this 3n factor will cancel with the denominator, and this 4 and 2 will cancel. You will get a 2 in the numerator. Now S is equal to nk log V plus nk log this h cube, you can write it into the bracket, and this becomes 2 pi mkt by h square raised to 3 by 2 plus 3 by 2 nk. I can write 3 by 2 nk from last two times outside, and remaining is 1 plus log 2 pi mkt by h square. So this term, this whole term in the square bracket, is independent of the size of the system. Independent of the size of the system. What is the meaning of that? If you increase the size of the system by a factor alpha, okay, the new size of the system is alpha times the size of old system. Then what happens to a number of particles? Number of particles will increase by a factor alpha. Volume will also increase by a factor of alpha. Then what happens to entropy of the new system? Let it be S alpha is equal to n alpha k log alpha V plus 3 by 2 alpha n k into 1 plus log 2 pi m kt by h square. Okay. Since entropy is an extensive property, any change in size should also reflect in the value of entropy also. That is, you should get S alpha equal to alpha S. But here you cannot take alpha outside from this log term. Okay. Since you have a term like log V, you will not get S alpha equal to alpha S. Okay. That is, if you apply this equation, or if you are taking this equation for entropy, you will not get entropy as an extensive property. But entropy should be an extensive quantity. So the problem is with the factor log V. Log V. If that log V is not there, everything is fine, because n will change to alpha n. This n will also be changed to alpha n. You can take alpha outside. That is, the new entropy will be alpha times old entropy. The other option is, if there is a log V by n, when this V changed to alpha V and n changed to alpha n, this log V by n will remain invariant, and due to the increase in n here and here, you will get S as alpha times old entropy. Then your equation will be correct. So either log V should be absent, or this log V should be log V by n. Okay, to make this entropy an extensive property. Another way to look at this problem is to consider the so-called Gibbs paradox. So I will explain what is Gibbs paradox in the next session. Gibbs paradox. So S is equal to nk log V plus 3 by 2 nk plus 3 by 2 nk log 2 pi m kt by h square. This is the equation we have in hand. Call this as equation 1. Now consider two ideal gases with same initial temperature. Okay, they are in two compartments. The first compartment contains a gas of N1 molecules, V1 volume and T temperature. The second compartment contains another gas with the N2 number of molecules, V2 volume and T temperature. What is entropy of the gas in the first compartment? It is S1 equal to, put all n as n1 in this equation 1, n1k, and put v as v1, n1k log v1 plus 3 by 2 n1k into 1 plus log 2 pi m1 kt by h square. Suppose the mass of molecules in this compartment is m1 and mass of molecule in the second compartment is m2. So S2 is equal to n2k log V2 plus 3 by 2 n2k into 1 plus log 2 pi m2 kt by h square. So total entropy at initially the total entropy can be written as Si equal to S1 plus S2, that is the sum of these two, n1k log V1 plus n2k log V2 plus 3 by 2 n1k into 1 plus log 2 pi m1 kt by h square plus 3 by 2 n2k 1 plus log 2 pi m2 kt by h square. Call this as equation. This is equation A. Then call this as equation 1. Now mix the two gases by removing the partition. Remove this partition. Then this gas will get mixed. Then this gas will get mixed. Then final entropy, you can write it as ST, total entropy of the system. ST is equal to, what is the number of particles? There is no partition. This is a single system consisting of N1 plus N2 particles. So instead of this N in equation A, you will have N1 plus N2. K log, instead of this V, what is the total volume of this compartment? V1 plus V2 plus 3 by 2. This n becomes n1 plus n2 into k plus the last term, you cannot write it as 3 by 2 n1 plus n2 because these are two different gases. So you have to write it separately. 3 by 2 n1k log 2 pi m1 kt by h square plus 3 by 2 n2k log 2 pi m2 kt by h square. Equation number 2. Delta S, change in entropy during this mixing process. Delta S is equal to final entropy St minus initial entropy Si. Delta S is equal to subtract this St minus Si. Okay. So this last two terms 3 by 2 n1k, this term will cancel with this term. This last term will cancel with this one. Okay. So this logarithm terms will cancel. Logarithm of 2 pi m1 kt by s square എന്നുള്ള time cancel ആയി പോകും. Remaining is n1 plus n2 k log v1 plus v2 minus n1k log v1 minus n2k log v2. This is the remaining thing. All other will cancel. So delta is equal to, this I can write it as n1 into k log v1 plus v2. Here I have n1 k log v1. Take n1 outside, then the first term will be k log v1 plus v2. This term will be minus k log v1. Similarly, you have here n2 into k log v1 plus v2. Here n2 k log v2. Take n2 outside, you will get like this. Then n1 into k log a minus b is log a by b. So log v1 plus v2 by v1. Similarly, in the second term, you have log v1 plus v2 by v2. This term v1 plus v2 by v1 is a positive quantity. Log of that quantity is again positive. So n to n1k. Everything is positive. So this whole quantity will be greater than 0. It will be a positive quantity. So delta S, the change in entropy is positive. The mixing of two dissimilar gases, is actually an irreversible process. If you if you put the partition back, the system will not be in the initial state. Okay, system will not be in the initial state. ഇവിടെയുള്ള കുറേ gases ഇവിടെയുള്ള കുറേ gases ഇവിടെ ആയിട്ടുണ്ടാവും. Okay, so you cannot take back this process to the initial stage. So it is an irreversible process. For an irreversible process, the entropy change is always greater than 0. So as such, there is no problem. Now, let the initial particle density is also same. Particle density means number of particles per unit volume. For the first compartment, it is n1 by v1. Second compartment, it is n2 by v2. Both compartments have same particle density, means these are equal. So I can write it as n1 by n2 equal to v1 by v2. Take n2 to the denominator, this v1 to the numerator. Then add a 1 on both sides. Take LCM, you will get n1 plus n2 by n2 equal to v1 plus v2 by v2. Similarly, if you write it in the inverse form, n2 by n1 equal to v2 by v1, and by adding 1, you can prove that n1 plus n2 by n1 is equal to v1 plus v2 by v1. So in the previous equation, for v1 plus v2 by v1, you can write it as n1 plus n2 by n1. For v1 plus v2 by v2, you can write it as n1 plus n2 by n2. So you can write it in terms of number of particles. This is equation 2. Again, these two terms are positive, so delta S is again greater than 0. So in terms of volume or in terms of number of particles, you can express delta S. In both cases, it is greater than 0 and it is an irreversible process also. So everything is fine. Now, consider mixing of two identical gases. Okay, consider mixing of two identical gases. Then what will be the change in equations? M1 will be equal to M2. Okay, M1 will be equal to M2. Both containers have the same molecules. Okay, contains the same molecule. Then same initial temperature, same particle density, and same molecules. So if you remove the partition, some molecules will pass one molecule from this compartment may go to the other compartment. The molecule from the first compartment may go to the second compartment. But eventually, when you put back the partition, number density, temperature, all things will remain the same as the initial state. Okay, the only difference, maybe some of the molecules in this compartment may reach here and the same number of molecules will reach here. Since they are all the same molecules, there is no difference between the initial stage and the final stage. That is, it is completely a reversible process. Okay, the mixing of two similar gases is a reversible process. And we already know from thermodynamics that for a reversible process, delta S, change in entropy, should be 0. Change in entropy should be 0. But using equation 2, what is equation 2? This one. This equation. This equation, if the gases are same, the only difference is this M1 becomes M, this M2 becomes M. And in the ST also, this M1 becomes M and M2 becomes M. When you take the change in entropy ST minus SI, this term will again cancel. Okay, irrespective of whether it is M1 and M2 or both are same, this term will cancel. Okay, this term will cancel. So the change in entropy, you will get the same relation, and as per this relation, entropy still is greater than 0. But from thermodynamics, we knew that delta S should be 0 for a reversible process. Here, we obtained it as delta S greater than 0. This discrepancy is called Gibbs paradox. This is called Gibbs paradox. Okay, on mixing of two similar gases, entropy change should be 0. But as per the entropy relation we have in hand, that is equation A, delta S is greater than 0. So that is called Gibbs paradox. So there is some fundamental issue with our relation for entropy. Okay, the relation A has some fundamental problems. Okay, so how can we fix that problem? That is the next case, remedy for Gibbs paradox. We have delta S equal to k n1 log n1 plus n2 by n1 plus n2 log n1 plus n2 by n2. This is our delta S. I can write it as delta S equal to k into n1 log n1 plus n2 by n1. I can write log n1 plus n2 minus log n1. Okay, then plus n2 into, again here also log n1 plus n2 by n2 can be written as log n1 plus n2 minus log n2. Log a by b is log a minus log b. This is nothing but k into this n1 log n1 plus n2 and n2 log n1 plus n2. Log n1 plus n2 is common, so remaining is n1 plus n2 minus n1 log n1 minus n2 log n2. This is n2 log n2. Now this is delta is equal to k into this term. I can write it as log n1 plus n2 factorial plus n1 plus n2, because we already have Stirling's formula. Log n factorial is n log n minus n. log n factorial is n log n minus n. This implies n log n is log n factorial plus n. This minus n will go to the left hand side. So log n factorial plus n എന്ന് എഴുതാം n log n. That is n1 plus n2 log n1 plus n2 can be written as log of n1 plus n2 factorial plus n1 plus n2. Similarly, minus n1 log n1 can be written as log n1 factorial plus n1. Okay. Minus n2 log n2 can be written as log n2 factorial plus n2. This terms n1 plus n2 will cancel with this minus n1 minus n2. Okay, this is plus n1, you will have a minus n1 here. This is plus n2, you will have a minus n2 here. That will cancel. Remaining is delta s is equal to k into log n1 plus n2 factorial minus log n1 factorial minus log n2 factorial. Call this as equation 2a. Okay, I rewrite this delta s in alternate form like a factorial form. Okay, it is the same equation 2 തന്നെയാണ്, but I rewrite it in a different form. Now let our expression for entropy is diminished by a factor of k log n factorial. K log n factorial. If our entropy is diminished by a factor of k log n factorial, that is the number of microstates reduced by a factor of n factorial. Entropy എങ്ങനെയാണ് നമുക്ക് ആ ഒരു ഇത് ഇൻഡ്യൂഷൻ കിട്ടുന്നതെന്ന് ചോദിച്ചു കഴിഞ്ഞാൽ, ഇവിടെ വന്നിരിക്കുന്ന ടേം ഡെൽറ്റ എസ് ഇത് 0 ആവണമായിരുന്നു. സിമിലർ ഗ്യാസസ് മിക്സ് ചെയ്യുമ്പോൾ ഡെൽറ്റ എസ് 0 ആവണമായിരുന്നു എന്ന് പറഞ്ഞാൽ ഈ സാധനങ്ങളൊക്കെ വാനിഷ് ചെയ്ത് പോകണം. അപ്പൊ നമ്മളുടെ എൻട്രോപ്പിയുടെ ഇക്വേഷനകത്ത് കെ ലോഗ് എൻ ഫാക്ടോറിയൽ എന്നൊരു ടേം മൈനസ് ചെയ്യാനുണ്ടായിരുന്നുവെങ്കിൽ ഇവരെയൊക്കെ ക്യാൻസൽ ചെയ്ത് കളയാൻ പറ്റുമായിരുന്നു. എൻട്രോപ്പിയുടെ ഇക്വേഷനകത്ത് ഒരു കെ ലോഗ് എൻ ഫാക്ടോറിയൽ കുറയ്ക്കുകയാണെങ്കിൽ, എൻട്രോപ്പിയുടെ ഇക്വേഷനിൽ കെ ലോഗ് എൻ ഫാക്ടോറിയൽ കുറയ്ക്കണമെങ്കിൽ നമ്പർ ഓഫ് മൈക്രോസ്റ്റേറ്റ്സ് എങ്ങനെ ആയിരിക്കണം? സപ്പോസ് യുവർ നമ്പർ ഓഫ് മൈക്രോസ്റ്റേറ്റ്സ് ഈസ് സംതിങ് ലൈക്ക് ഒമേഗ സ്റ്റാർ ഈക്വൽ ടു ഒമേഗ ബൈ എൻ ഫാക്ടോറിയൽ. നമ്മൾ ഇപ്പൊ കൺസിഡർ ചെയ്തിരിക്കുന്നത് ഒമേഗ എന്നാണ്. Suppose the correct equation is omega star equal to omega by n factorial. Then entropy, correct equation for entropy S star equal to k log omega star. K log omega star. It is k log omega star is nothing but omega by n factorial. So this can be written as k log omega minus k log n factorial. K log omega is the previous expression for entropy. Already we have this expression k log omega as entropy. So the new entropy S star is S minus k log n factorial. Okay. So നമ്മൾ എൻട്രോപ്പിയുടെ ഇക്വേഷനകത്ത് ഒരു k log n factorial കുറയ്ക്കുന്നു എന്ന് വിചാരിക്കുക. ഇതാണ് കറക്റ്റ് എക്സ്പ്രഷൻ എന്ന് നമ്മൾ ക്ലെയിം ചെയ്യുകയാണെങ്കിൽ നമ്മളുടെ ഡെൽറ്റ എസ് സ്റ്റാർ, ഈ പുതിയ സ്റ്റാർ ഇട്ടതാണ് നമ്മൾ പുതിയ എൻട്രോപ്പി എന്ന് ക്ലെയിം ചെയ്യുന്നത്. എസ് ആണ് നമ്മളുടെ തെറ്റായ ഇക്വേഷൻ. മൈനസ് കെ ലോഗ് എൻ ഫാക്ടോറിയൽ, ഇങ്ങനെ ഒരു ടേം മൈനസ് ചെയ്തുകൊണ്ട് അതിനെ കറക്റ്റ് ചെയ്യാണ് ആ ഇക്വേഷൻ. എങ്കിൽ what will be delta change in entropy for the new defined quantity delta S star? It will be St star final entropy star minus S1 star plus S2 star initial entropy. Delta S star equal to this St star, I can write it as St minus k log n1 plus n2 factorial, because for the combined system number of particles is n1 plus n2. So a diminishing factor k log n factorial become k log n1 plus n2 factorial minus S1 star become S1 minus k log n1 factorial. S2 star becomes S2 minus k log n2 factorial. Okay. Then delta S star equal to this St minus S1 minus S2 combined together, you can write it as St minus of S1 plus S2. Then minus k log n1 plus n2 factorial minus minus plus k log n1 factorial minus minus plus k log n2 factorial. St minus S1 plus S2 is actually delta S. This is our previous version of delta S. This is new version delta S star. There is a term minus k log n1 plus n2 factorial plus k log n1 factorial plus k log n2 factorial. If you substitute delta S from equation 2a, then you will get it as k k log n1 plus n2 factorial minus k log n1 factorial minus k log n2 factorial minus these terms k log n1 plus n2 factorial plus k log n1 factorial plus k log n2 factorial. All these terms will cancel and you will get delta S star as 0. So if you redefine entropy as S minus k log n factorial, this new entropy will satisfy that change in entropy for a reversible process should be 0. Okay? Change in entropy for a reversible process 0 ആയിരിക്കണം എന്നുള്ള കണ്ടീഷൻ ഇത് സാറ്റിസ്ഫൈ ചെയ്യുന്നുണ്ട്. അപ്പോൾ നിങ്ങൾ എൻട്രോപ്പിയുടെ ഇക്വേഷൻ എങ്ങനെ മോഡിഫൈ ചെയ്താൽ മതിയാവും? ഒരു മൈനസ് കെ ലോഗ് എൻ ഫാക്ടോറിയൽ ചേർത്താൽ മതി. അപ്പോൾ ഡിസിമിലർ സിസ്റ്റത്തിനാണെങ്കിൽ അത് സാറ്റിസ്ഫൈ ചെയ്യാൻ നോക്കാം. ഡിസിമിലർ സിസ്റ്റത്തിന്റെ കേസിൽ നമ്മൾ നമ്പർ ഓഫ് മൈക്രോസ്റ്റേറ്റ്സ് ഓഫ് കമ്പൈൻഡ് സിസ്റ്റം എഴുതുന്ന സമയത്ത് ഒമേഗ ടി സ്റ്റാർ, ഓക്കെ, സ്റ്റാർ എന്ന് പറയുന്നത് നമ്മൾ മോഡിഫൈ ചെയ്ത നമ്പർ ഓഫ് മൈക്രോസ്റ്റേറ്റ്സ്, ദാറ്റ് ഈസ് ഒമേഗ 1 സ്റ്റാർ ഇൻറ്റു ഒമേഗ 2 സ്റ്റാർ. രണ്ട് സിസ്റ്റങ്ങൾ, ഒന്നാമത്തെ സിസ്റ്റത്തിന് ഒമേഗ 1 സ്റ്റാർ മൈക്രോസ്റ്റേറ്റ്സ് എടുക്കാം. സെക്കൻഡ് സിസ്റ്റം ക്യാൻ ഹാവ് ഒമേഗ 2 സ്റ്റാർ മൈക്രോസ്റ്റേറ്റ്സ്. Then the combined system, the number of microstates will be the product of the two. So that is omega 1 by n1 factorial, omega 2 by n2 factorial. That is omega t. Omega 1, omega 2 is the old number of microstates, omega t divided by n1 factorial, n2 factorial. So st star, the new defined entropy is st old entropy minus k log n1 factorial, n2 factorial. For the first compartment, it is S1 star equal to S1 minus k log n1 factorial, S2 star equal to S2 minus k log n2 factorial. If you substitute here St star minus S1 star plus S2 star, it is nothing but delta S star. It is equal to St minus, this St star is St minus k log n1 factorial, n2 factorial minus S1 star is S1, this minus and this minus becomes plus k log n1 factorial minus S2 star is S2, minus and minus becomes plus k log n2 factorial. So delta S star equal to St minus this S1, this S1, S1 plus S2 minus k log A into B is log A plus log B. So this due to this minus, both the terms will be negative. Here you have two positive terms. All this will cancel and delta S star is equal to delta S. Okay. ഇവിടെ നിങ്ങൾക്ക് ഇത് വെട്ടിപ്പോവുള്ളൂ. ഡെൽറ്റ എസ് സ്റ്റാർ ഡെൽറ്റ എസ് ആയിട്ട് തന്നെ കിട്ടും. ആൻഡ് ഡെൽറ്റ എസ് is we already know that it is greater than 0. So for dissimilar systems we will get the old expression delta is greater than 0 and delta S star is also greater than 0. For similar systems you will get delta S star is equal to 0 for identical system. So our problem is solved. Mixing of two dissimilar gases is a irreversible process and we will get a positive entropy change. Mixing of two similar gases is a reversible process and we will get entropy change as 0. Okay. So what is our remedy? That new equation for entropy is called the Sackur-Tetrode relation and it is obtained from the old one by subtracting a k log n factorial. This is your old equation, nk log v by h cube 4 pi me by 3n whole raised to 3 by 2 plus 3 by 2 nk. Subtract a k log n factorial. What is k log n factorial? Log n factorial is n log n minus n. So when you substitute that here, you will get it as minus nk log n plus nk. Then this 3 by 2 nk plus nk becomes 5 by 2 nk. And nk log v by h cube, here you have nk log n with a negative sign. Nk is take as common. Then log a minus b is log a by b. So you will get a n in the denominator. So it is s equal to nk log v by n h cube to 4 pi me by 3n raised to 3 by 2 plus 5 by 2 nk. Okay. This expression, or as per this equation, entropy is an extensive quantity. Why? Because in the inside bracket you have a v by n. V by n is an intensive property. V by n doesn't depend on the size of the system. As you increase the size, V increases, at the same rate n will also increase. So V by n will remain invariant. Similarly, E by n is also an intensive property. E depends on the size of the system. E is directly proportional to size of the system. N is directly proportional to size of the system. But E by N is invariant with respect to size of the system. So all the terms inside the logarithm is intensive properties. So when you increase the size of the system, this n becomes alpha times n and this n becomes alpha times n. So you can take alpha as common. So this entropy will also increase by a factor of alpha. So this expression, equation number 3 for entropy, if you use this expression for entropy, you will get entropy as an extensive quantity. But if you use this relation without this kn factorial, k log n factorial, that will not be an extensive quantity. So our problems are solved, and this equation for entropy is called the Sackur-Tetrode equation. Now you can invert this equation for obtaining an expression for energy. You multiply this equation with 2 by 3 and divide with nk. Okay, and this becomes 5 by 3 and take it to the left hand side. So 2s by 3 nk, 2s by 3 nk minus 5 by 3 equal to, okay, our aim is to express energy in terms of n, v and s. So invert this equation. For that, multiply with 2 by 3, divide with n by k and take this term to the left hand side. Okay, then rearrange this to obtain E as ESVN equal to 3h square n raised to 5 by 3 divided by 4 pi m v raised to 2 by 3 e raised to 2s by 3 nk minus 5 by 3. As per this equation, E is also extensive because this n raised to 5 by 3 divided by v raised to 2 by 3, that will give me an n in the numerator. Okay, ഇത് നിങ്ങൾ എക്സ്റ്റൻസീവ് ആയിട്ട് കൺസിഡർ ചെയ്യുകയാണെങ്കിൽ ഇതിന്റെ എൻ ബൈ വി എന്നുള്ള ഫാക്ടറിൽ ഒരു 2/3 ഫാക്ടർ പോയി കഴിഞ്ഞാൽ ദർ ഈസ് എൻ ഡിപെൻഡൻസ് ഫാക്ടർ ഓൺ ദി ന്യൂമറേറ്റർ. Okay, that means if you increase this n by alpha n, that becomes alpha n raised to 5 by 3. That v will become alpha v raised to 2 by 3. So that will give me an alpha in the numerator. So energy will be increased by that factor. So that energy is extensive quantity. Now we can derive all the remaining thermodynamic parameters using this expression for energy. Chemical potential mu is dou E by dou N. Okay, before that I will make a remark. The thermodynamic parameters we derived in the first session of this lecture, all that parameters will remain unchanged even if we use equation 4. Okay, നമ്മൾ ഈ ലെക്ചറിന്റെ തുടക്കത്തിൽ കുറച്ച് തെർമോഡൈനാമിക് പ്രോപ്പർട്ടീസ് ഡെറൈവ് ചെയ്തിരുന്നു. Okay, all these derivations were made from this equation for energy, equation 1. If we use the equation for energy, this one, equation 4, all those parameters will remain invariant. All those parameters that we derived there will remain invariant. Now we can derive few more quantities, thermodynamic parameters. One is chemical potential mu, that is dou E by dou N Vs. For this, we have to use this expression 4. If we use equation 1, you will get a wrong result. So chemical potential കാണാനായിട്ട് നിങ്ങൾക്ക് equation 4 തന്നെ യൂസ് ചെയ്യണം. കാരണം നമ്പറിനകത്ത് വ്യത്യാസം വന്നിട്ടുണ്ട്. നേരത്തെ equation 1-ലുള്ള നമ്പർ ഡിപെൻഡൻസ് അല്ല ഇവിടെ. So take derivative of this expression with respect to n. There is two n dependent terms. One is n raised to 5 by 3, the other one is in the exponential term. So you will get two times for the derivative. This n raised to 5 by 3 derivative is 5 by 3 n raised to 2 by 3. All other things constant. Plus take the derivative of exponential. Then you will get exponential into 2s by 3 nk. Derivative is 2s by 3k is constant. 1 by n derivative is minus 1 by n square. Rearranging this, you can write it as mu is equal to 5e by 3n minus 2es by 3k n square. Equation number 5. You can rewrite it as mu is equal to 1 by n into 5 by 3e minus 2 by 3 nk into es. But e is 3 by 2 nkt, e is 3 by 2 nkt, pv is 2 by 3e. So 5 by 3 I can write it as e plus 2 by 3e. So e plus pv. Then substituting for this E as 3 by 2 n kt, we will get it as minus Ts. So mu is equal to 1 by n into E plus PV minus Ts. What is E plus PV minus Ts? E plus PV minus Ts is nothing but Gibbs free energy. So chemical potential mu is equal to Gibbs free energy per particle. G by n is Gibbs free energy of the system per particle. There are n particles, total Gibbs free energy is G. So G by n is the Gibbs free energy per particle. So you can say that the chemical potential of a system is the Gibbs free energy per particle. Now you can write this mu as a function of T, V and n, temperature, volume and n. Here this mu is a function of energy and entropy. You can express energy in terms of temperature as 3 by 2 n kt. You can express entropy using this relation, Sackur-Tetrode relation. Then you will get mu as substitute these values for E, substitute 3 by 2 n kt minus T into, for S you substitute the equation Sackur-Tetrode relation and solve this. You can show that mu of T V n, okay, just one step, okay, kt log n by v into h square by 2 pi m kt all raised to 3 by 2. Now Helmholtz free energy F is equal to E minus Ts and that is equal to G minus PV, and G is nothing but mu n, PV is nkt using ideal gas equation. So F is equal to mu n minus nkt, but this mu is kt log this quantity. So you will get it as nkt, you can take it outside, then log n by v h square by 2 pi m kt raised to 3 by 2 minus 1. This is Helmholtz free energy. This Helmholtz free energy is also an extensive property because it depends on n. So F is an extensive property, but mu is intensive. See, in mu there is no factor which depends on the size of the system. Here there is an n, here there is an n, but there is a v also. So that n by v becomes intensive. Now we'll discuss what is the method of correct enumeration of microstates. Okay, we already seen that if we correct the microstates by dividing with an n factorial, then we can solve all the problems associated with the entropy relation. So what is the physics behind this division by a factor of n factorial? Suppose we have n particles distributed in various energy levels and having a total energy E. Then suppose there are n1 particles with energy E1, n2 particles with energy E2, n3 particles with energy E3 and so on. Then the macrostate is defined as sigma Ni is equal to capital N. Total number of particles should be capital N and total energy sigma NiEi should be capital E. This defines a macrostate. For this particular macrostate, how many microstates are there? For that, we can consider different distribution sets. For satisfying this particular condition, we will have different distribution sets. Suppose one such distribution is this one. N1 particles in first state or first level, N2 particles in the second level and so on. Suppose this is one of the distribution. Then corresponding to a distribution, what are the number of microstates? What is the number of microstates? It is given by n factorial divided by these numbers n1 factorial, n2 factorial, n3 factorial, etc. if the particles are distinguishable. And the number of microstates in a distribution is always 1 if particles are indistinguishable. Particles indistinguishable ആണെങ്കിൽ number of microstates in a possible distribution is 1. What is the meaning of this statement? I will explain that using this graph. This graph I already explained in the first lecture of this series. This is the case for 4 particle system. N is equal to 4 and energy, total energy is 6 epsilon. I have 4 single particle energy levels with energies 0, epsilon, 2 epsilon and 3 epsilon. And I have 4 particles. Suppose initially these particles are distinguishable. These particles are distinguishable. That is, I have four particles. I can denote it as A, B, C, D. Then if two particles A and B lying on this energy level with energy epsilon, C and D lying in the energy level with energy 2 epsilon, total energy will be 6 epsilon. So this is one of the possible distribution. That is, distribution can be denoted as 0, 2, 2, 0. In the lower level 0 particle, at next level 2 particle, next level 2 particle, and next level 0 particle. So this distribution is 0, 2, 2, 0. In this graph, this first point is 0, 2, 2, 0. How many number of microstates associated with this particular distribution? You can place A and C in the lower level, B and D in the top. That will again give you same distribution 0, 2, 2, 0 with the same energy, total energy 6 epsilon. But that is a distinct microstate, A and C in the denominator, because these particles are distinguishable particles. In a similar manner, you can think of six possible ways. Six possible ways. A, B in the lower level, A, C, A, D, B, C, B, D, C, D. So six possibilities. How can we get that six? By writing this equation. 4 factorial by 0 factorial into 2 factorial into 2 factorial into 0 factorial. This will give you a 6. In a similar manner, another distribution is 2002 for this particular microstate. Then you will get the number of microstate in this distribution as 6. For 1111, for this distribution, you will get number of microstates as 24. And in a similar manner, for the possible 5 distributions, you can find the number of microstates. That is the meaning of this expression for finding number of microstates of a distribution if particles are distinguishable. What happens if these particles are not distinguishable? That is, indistinguishable particles. All the particles are identical. All the particles are identical. Then this is all these are identical particles. Then if you interchange two particles, then that doesn't make any difference. All those are corresponding to the same microstate. All these are corresponding to the same. So for this particular distribution 0, 2, 2, 0, there is only one microstate. There is only one microstate. So for all these 5 distributions, microstates, number of microstates will be 1. If you consider another distribution, say 1, 1, 2, 0, that is not a possible distribution for this microstate, then the number of microstates will be 0. That means for indistinguishable particles, the number of microstates for a distribution is either 0 or 1. Is either 0 or 1. But for a distinguishable particles, for a distinguishable particle, number of microstates for a distribution is n factorial by n1 factorial, n2 factorial, n3 factorial, etc. So this is the number of microstates calculation. So particles indistinguishable ആവുന്ന സമയത്ത് number of microstates വളരെ വലിയ രീതിയിൽ റെഡ്യൂസ് ചെയ്യപ്പെടും. ഈ റിഡക്ഷൻ ആണ് ബൈ n ഫാക്ടോറിയലും കൊണ്ട് ഗിബ്സ് കറക്റ്റ് ചെയ്തത്. So Gibbs wrote omega, nu omega as omega divided by n factorial. So in our case, this distribution number of microstates in a particular distribution, omega of ni, you divide it with ni, then this ni will cancel in the numerator and denominator. You will get it as 1 by n1 factorial into n2 factorial into n3 factorial. So for indistinguishable particles, you have to use this. Indistinguishable particles, you have to use this expression for finding number of microstates associated with a distribution. That is the remedy proposed by Gibbs. But this is also wrong if n2, n3, etc. are greater than 1. If any of this number, n1, n2, n3, any of this number, ഏതെങ്കിലും ഒരെണ്ണം is greater than 1, then this will be wrong. Because for indistinguishable particles, for W, we should get either 1 or 0. If it is a possible distribution, you should get 1. If it is not a possible distribution, you should get 0. Only these two possibilities, either 1 or 0. But if n1, n2, n3, if all these are either 0 or 1, If n1 into n3 can take only 0 or 1, then you will get definitely a 1. I will show this here. You have 9 energy levels and only 6 particles. Okay, so one particle sits here. In the next level there is no particle. One particle here, one particle. So this is a distribution. What is W? 1 divided by here 1 factorial, 0 factorial, 1 factorial, 1 factorial, 0 factorial, 1 factorial, 1 factorial, 1 factorial, 0 factorial. 0 factorial is 1, 1 factorial is 1, so you will get it as 1. But if the particle density is high, 9 levels and 13 particles. In some of levels, there are 2 particles. Okay, that can be 3 also. Okay, now in this figure, in some levels, there are 2 particles. Then what is W? 1 divided by 1 factorial into 2 factorial into 2 factorial into 1 factorial into 2 factorial into 1 factorial, etc. So this will be 1 by 16. That is not equal to 1. Okay, for indistinguishable particles, this W should be either 1 or 0. So, if any of the level occupies more than one particle, this equation also went wrong. So, what is our claim? For low density and high temperature, this equation can apply. Because if the density is very low, maximum one particle will sit in a level. Okay, so this numbers n1, n2, n3, etc. will be maximum of 1. If the density of particle is more, one level can occupy by more than one particle. Then this will went wrong. So we can safely use this expression 1 by n1 factorial, n2 factorial, n3 factorial, etc. at high temperature and low density, or when the occupation number is very much less than 1. Here you can see that occupation number is, there are 6 particle and 9 levels, so occupation number is roughly 0.67. It is a measure of average occupation number. Here it is greater than 1. If you have more particles than the number of energy levels, occupation number will be greater than 1. So this expression is true only when occupation number is very much less than 1, and that defines a classical limit for the problem. Okay, so thank you.